Okay, so let us start now. So in the last class, we were discussing about the different parameters associated with engine performance, combustion and emission. So particularly when we are discussing about, all right, we discussed that in engine, we have a major three subsections. When we are discussing about internal combustion engine, or we are studying about the internal combustion engine, so there are mainly three different subsections, in which we have to study about the what is the performance of the engine, the combustion, and the third one is the emission. All three sections are interrelated with each other. It means if you change one parameter, then it is going to affect all three sections, subsections, either in a favorable manner or it is negative manner. So let us discuss. We discuss about the engine performance parameter, in which we discussed that what is about the indicated thermal efficiency. So first of all, it is a thermal efficiency. So what is indicated thermal efficiency? Brake thermal efficiency, volumetric efficiency, mean effective pressure, mean piston speed, fuel consumption, air fuel ratio. So indicated thermal efficiency or thermal efficiency, we define that as efficiency is defined with the input or output divided by input. So in engine, we have input in terms of the mass flow rate of the fuel into the calorific value of the fuel. So that will give us how much energy you are giving as the input, and the output depending upon where you are measuring the pressure. If you are measuring the where you are measuring the power output, if you are measuring the power at the piston surface, that how much the force is acting on the piston surfaces by the combustion, then it will give you the indicated power, and then correspondingly it is called indicated thermal efficiency. If you are measuring the power output as the flywheel in the engine, that can be measured using the dynamometer, then it will give you the brake power, and then the corresponding thermal efficiency we discussed about, it is called brake thermal efficiency. Mechanical efficiency is the ratio of the brake thermal efficiency to the indicated thermal efficiency. Brake indicated thermal efficiency is always higher than the brake thermal efficiency, because when the power is transmitting from the piston to the flywheel, then there is some losses in terms of mechanical losses, transmission loss or coolant loss. So many kind of the losses is there. So therefore, when you are getting the useful power, that is the brake power, that is always lower than the indicated power. Then we were discussing about the volumetric efficiency. What is called volumetric efficiency? So that is the ratio of actual air flow rate divided by theoretical air flow rate. So theoretical air flow rate, it means the maximum capacity of the engine that can accommodate the air. And it can be calculated like that, displacement volume into the density of the air, that will give the mass, and mass flow rate. To calculate mass flow rate, we are going to multiply with the engine RPM divided by 2, because we are considering it is a 4-stroke engine. If it is a 2-stroke engine, where there will be one intake stroke per revolution of the crankshaft, then it will become only N. So in that way, we can calculate that what is the capacity of the engine to accommodate the air at a given speed of the engine. That will give us the theoretical air mass flow rate. And then we need to measure the actual mass flow rate. And then we will take the ratio of these two, actual divided by theoretical, that will give you the volumetric efficiency of the engine. It is a very important parameter, because volumetric efficiency is giving you the indication that how efficient your engine is accommodating the air. Accordingly, you can inject the fuel, and then when the ratio of the fuel and air is going to 1, then it will give the power output. If the air volume, if the air inside the combustion chamber itself is very low or a small, then we cannot inject just the fuel to get the more power output, because we need to have oxidizer also. So therefore, the volumetric efficiency of the engine is very important, and its importance is even much more in the spark ignition engine. Because what we discussed, that in a spark ignition engine, we use throttle in the intake manifold, or in fact, we throttle the incoming air, and therefore the manifold pressure or the pressure in the downstream of the throttle is always less than the atmospheric pressure, and it decreases the volumetric efficiency of the spark ignition engine. If you remember, we discussed that volumetric efficiency of the spark ignition engine can vary from around 20% to around 75 to 80% max, depending upon the how much throttle is opened. Whereas the volumetric efficiency parameter is not so critical in the diesel engine, because there is no throttle in the intake manifold, and the air comes from the atmosphere into the combustion chamber without any restrictions. So the volumetric efficiency of the diesel engine is always around 82, 87, 88, or max, let us go up to the 90%. And remember, all these things we are talking when engine is a natural aspirated engine. It means the engine is sucking the air only because of the movement of the piston. So the volumetric efficiency of the diesel engine is always very good, or even you can say it is higher even than the spark ignition engine. We also discussed that how we can measure the mass flow rate of the air, actual mass flow rate of the air in engine application. So all of you have suggested some of the methodology. Yes, that can be used. OK, as far as the in terms of the if you are doing the experiments in the laboratory, then you have a flexibility of the space and you can use all sort of the equipment. But when you have to apply on the engine, where the space is one of the major constants, packaging of the whole system within the small volume is itself a big challenge. There, the mass flow rate of the air is measured either through the throttling method, depending upon the several information from the sensors, like what is the throttle is opened, how much throttle is opened, what is the intake manifold pressure, what is the intake manifold air temperature, engine speed, and the engine geometry. If your ECU, engine control unit, is getting all sort of this information, then ECU either it can calculate online what is the mass flow rate of the air, that is normally not happened. In fact, in the engine, what happens that there is a lookup table already stored in the ECU, that depending upon the engine input parameters, ECU will trace that according to this engine speed and the throttle opening and manifold pressure, whatever the way how it has been stored, what is the mass flow rate of the air. Because engine is a very dynamic phenomena where you can calculate that if the engine is running, let's suppose at 4000 RPM, then how much time it will take in one cycle. And then you can find it out in one cycle at 720 degree. In 720 degree, it is approximately 200 degree crank angle is the intake, or slightly more intake strokes. So how your electronic system is going to act fast enough to calculate the mass flow rate of the air, and then correspondingly engine has to inject the fuel also. So it depends upon the several how this parameter is measured in the engine. It depends upon the algorithm and the um, uh, how the ECU has been calibrated. But in the laboratory, you can measure it through the orifice meter. That is the simplest and the basic fundamental methodology that you can install one orifice meter in the intake manifold, measure the pressure difference across the orifice, apply the Bernoulli's theorem, and measure the what is the mass flow rate of the air. Or the second methodology is that, or even you can utilize in the lab or in the vehicle also, that you can install one of the sensor that is normally used in the production engine, that is called hot film anemometry sensor. Hot film anemometry sensor, HFM, hot flow airflow meters, which will give you directly it will give you the mass flow rate of the air. So there are different methodology that experimentally you can measure the actual mass flow rate of air. You know the geometry of the engine and the engine speed. You can calculate the theoretical mass flow rate of the air, and then you can have the volumetric efficiency. Yeah, one of the very important things I also pointed out that when you are designing the engine, particularly the spark ignition engine, so your major motive is to how to improve the volumetric efficiency of the engine so that we can get the more power output, or how the volumetric efficiency can be flattened over the larger. Sometimes you have seen that engine speed. OK, if you see the technical specification of the engine in any vehicle, you will find it out that maximum torque. OK, let us suppose we are talking about Maruti Alto K10 engine. OK, that will give around 90 Newton meter torque at around 3000 to 3500 RPM. Below that or above that, the range, the torque output will reduced. Similar power, maximum power, you may get it around something in the range of the speed of 4500 to 5000 RPM. So have you ever think that why the engine is producing the maximum torque output within a narrow range of the speed, and below or lower than that speed range or the above, the torque output is less? Is there any possibility that we can widen the range of the speed where we are getting the maximum torque output or maximum power output? How we can widen it? Why it is restricted? That is really very important things as of now, that because everyone wants to have a very high torque even at the low speeds or more power of the engine. So how we can widen it? That all these things you think about that why it is happening. Obviously, this answer of these questions we are going to get it towards the end of this course, but these are the things I'm pointing out right now, and think about that. Similarly, there is in terms of the fuel consumption, there is a two parameter is specified. One is called indicated specific fuel consumptions, that is ISFC, or brake specific fuel consumption, that is BSFC. OK, it is what is it that it represents that how much fuel is required in order to produce 1 kilowatt of the power output. So the power, depending upon which power you are taking, if you are taking the indicated power, then it is going to be ISFC. If you are taking the power as a brake power, then it is going to be BSFC. So to calculate the BSFC or ISFC, we have to measure that for a given operating condition of the engine, or what is the mass flow rate of the fuel. Again, for the fuel consumptions, you also suggested that we can use the burette rate. We can measure the volume of the fuel to be consumed in a given time. That will give you the mass volume flow rate of the fuel, and multiply with the density of the fuel. It will give the mass flow rate of the fuel. Power, anyway, we were measuring it in the experiments. So you can calculate the specific fuel consumption, or instead of the volume flow rate of the fuel measurement, it is always better to use a kind of the equipment that will give you the mass flow rate of the fuel. Because when you are calculating the volume flow, where you are measuring the volume flow rate, then you have to multiply with the density of the fuel. And the density is the depending upon the your temperature. So if you are not taking a correct value of the density of the fuel at that time, at that temperature, then it will be a source of the error in your experimental results. So you can always better to measure if it is you have to measure the mass flow rate of the fuel. For that, obviously we need to use some kind of the sensor that will give you that will measure the mass of the fuel tank, a small fuel tank, that how it is varying over the time, and then it will give you the mass flow rate of the fuel consumption. Yeah, the third, another parameter that is really very important, particularly when you are talking about the internal combustion engine, is the air fuel ratio. There are different ways to characterize this parameter. Okay, air fuel ratio, we can say air fuel ratio or fuel air ratio, equivalence ratio, relative air fuel ratio, that is represented by lambda. Equivalence ratio, it is represented by 5. These are the very common practice in terms of the engine. What are all these things? That is, we need to understand in detail, and has to be very clear also. As we are measuring the fuel, how much fuel, let's suppose your engine is running at 2000 RPM and 20 Newton meter torque. So that speed and torque I have specified. And sometimes I always used a terms that is called operating condition of the engine. So when I'm saying operating condition of the engine, it means the engine speed and the torque is specified to you. So when the engine is running at a given operating condition of the engine, okay, your engine is equipped with several kind of the sensors. You have already studied or discussed that how we can measure the mass flow rate of the air and how we can measure the fuel flow rate of the air. So both variables or parameters is known to us. When we will take the ratio of these two measurable quantity, if we are taking the air divided by fuel, mass flow rate of the air divided by mass flow rate of the fuel, it will give the your air fuel ratio. Or in the reverse manner, mass flow rate of the fuel divided by the air mass flow rate of the air, it will give the fuel air ratio. So each fuel, okay, let us suppose we have a petrol, a gasoline, or CNG, or hydrogen, or ethanol, whatever the fuel. For a specific fuel, we have a particular air fuel ratio that is called chemically correct air fuel mixture, or stoichiometric mixture, air fuel mixture, where we assume that all the fuels are not assumed, where it is a correct mixture of the fuel and air. So to combust and give the product a product in terms of the CO2, H2O and nitrogen if we are taking the oxidizer as air. So therefore, we need to find it out for a given fuel that what is the stoichiometric air fuel ratio or what is the air fuel ratio. When engine is running, we have to also calculate what is the air fuel ratio. When we are talking about equivalence ratio, okay, you can see several book or any IC engine book or any IC engine paper, technical paper, you will find it out instead of the writing or giving the air fuel ratio or fuel air ratio, in the book or in the technical paper, they are using the parameter that is equivalence ratio or relative air fuel ratio that is represented by lambda. What is that? So it's nothing like any big things is here. Equivalence ratio is defined as the actual fuel divided by air ratio. It means we have to measure that what is the actual air mass flow rate and what is the actual flow rate of the fuel. And then we take the ratio of the actual fuel flow rate divided by actual mass flow rate. So that is what it is giving the actual fuel divided by air ratio. That is what it is written F by A actual. And for a given fuel, we need to find it out what is the stoichiometric air fuel ratio. So fuel by air S stoichiometric. The ratio of the actual fuel by air ratio to the stoichiometric air fuel by air ratio is called equivalence ratio that is defined by phi. Whereas relative air fuel ratio or lambda is defined in such a way that in equivalence ratio, we are taking fuel by air ratio. In lambda, it is going to be air by fuel ratio, nothing else. It is just the reciprocal. Phi and equivalence ratio are reciprocal with each other. So here in lambda, we are talking about fuel by air. Oh, I'm sorry. Lambda, we are taking air by fuel actual divided by air by fuel stoichiometric. Now, if the okay, just hold it and then we'll come back another way. So what we are talking about this equations, we done this kind of the practice, I hope, in your thermodynamics, that for a given fuel, let us that fuel is a hydrocarbons that contains carbon and hydrogen. OK, and it is oxidizing completely. That is what we are talking about stoichiometric combustion or chemically correct air fuel mixture. So there is a hydrocarbon that contains carbon and hydrogen and it is completely oxidized with the air. OK, here always remember we are talking about oxygen plus nitrogen. Then it will give you the carbon dioxide. After the product will be carbon dioxide, water and nitrogen. We are assuming that nitrogen is not participating in the combustion. This is the it's the ideal combustion equation. It is an ideal combustion equation where the fuel is complete combust with the presence of the air and then it is giving the carbon dioxide, water and nitrogen. In reality, it is not going to be happen like that. There are several kind of the products we are going to get it after the combustion. OK, but hold it right now. So for any hydrocarbon fuel, let us write down CHB and then air, oxygen plus 3.773 nitrogen, balance it both sides, and that will give you the complete equation. And then we can calculate that how much fuel will required, how much air will be required to burn 1 unit of the fuel, and that ratio, it is giving us the air fuel ratio. So let us suppose we have a fuel in terms of octane. OK, C8H18, C8H18 octane. Octane is considered as the very close, or we ideally we take octane whenever we have to deal with the gasoline fuel. OK, but it is anyway, gasoline has contains several hydrocarbons. So but let us take octane as a fuel, C8H18, and then find it out what will be the stoichiometric air fuel ratio. Take the fuel C8H18 and give me the ratio, that air fuel ratio. What is the air fuel ratio is coming? Kindly do it at your end. C8H18, we have a fuel, and we need to find it out what is the stoichiometric fuel or stoichiometric air by fuel ratio. Air by fuel ratio. Please calculate it. C8H18. OK. Oxidizer, take it as a air. Oxygen plus 3.773 nitrogen. Balance, and then product, take it as a carbon dioxide, water plus nitrogen. Balance the elements both sides, and then tell me how much it is coming. Air by fuel ratio. I'm giving to 3-4 minutes, and then I will call the name, and then please tell me. Your fuel is octane C8H18, and then you have to find it out air by fuel ratio for chemically correct air fuel mixture. Anyone who has completed?
Is it 12.5?
What is?
Is it 12.5?
12.5. How much you are saying?
12.5.
12 point. No.
Sir, 15.1.
Yeah. So, okay. Nilesh, have you done? Nilesh, are you there? Manu Sehgal? Okay, Nilesh, I got you. Manu Sehgal, are you there? If what I'm trying to find it out that at least all of you are comfortable to find it out the air chemical air fuel or stoichiometric air fuel ratio. If there is any problem to any one of you, then you have to come out and tell me. For C8 H18 octane fuel, what would be the stoichiometric air fuel ratio? Krishna Kant Rawat.
Yes, sir, still doing.
Okay, do it. Please do it. So if you write down the first of all, you write down the equation C8H18 plus oxygen O2 plus 3.773 nitrogen. And then product side you write down CO2 plus H2O plus nitrogen. And then balance the carbon, hydrogen and nitrogen. In order to do that, if you do the balancing, then what will come? The complete equation will come something like or I have already written here. If it is only carbon and hydrogen, then the coefficient is already written here. So you can use the help of this equation, also general equation. 8 plus how much? 18 plus 4. So it will come around 12.5. Am I correct?
Yes, sir.
Yeah. So it's 12.5 C8 H18 plus 12.5 O2 plus 3.773 nitrogen and then 8 CO2 9 H2O and then you just use it 3.773 into 12.5 nitrogen. So then find it out that how many moles per moles 1 mole of the fuel is required, how many moles of the air. So 12.5 into 4.773 moles of air is required. Then in terms of the weight and then take the ratio of that. And that will give you around 15.1. So your air fuel ratio that is going to come, it will come 15.1. It means 1 unit of the fuel will require 15 unit of air to have a complete combustion. And that ratio 15.1 is called a stoichiometric air fuel ratio. I hope everyone has done or there is still some problem. Okay, next problem. CNG. Okay, we use CNG. We are using CNG almost now every city, almost all the cities now we have a CNG. Not I would say almost all, but most of the cities we have a now CNG fuel. CNG is considered as it is mainly it contains the methane. So let us model the CNG as a 100% methane, CH4, and then tell me what will be the ratio. And this time I will call a particular name of the students and please that students has to give me the answer. Methane, that is CNG, compressed natural gas. Take CNG, CH4, consider as a methane. Find it out what is the stoichiometric air by fuel ratio. Methane. Don't leave the class. Do it. Saurabh Gupta, can you unmute yourself, please?
Yes, sir.
Are you doing?
Yes, sir.
Okay.
Sir, I'm trying to do. Yes, sir.
Okay, do it and tell me.
Yes, sir.
Take CH4. Similar way, take the air. And then product carbon dioxide, air, nitrogen, the similar way that we discussed for octane. Balance it. First of all, find it out in terms of the mole. Then in terms of the mass. And then take the ratio. That is the what's very simple. Siddhartha, are you there?
16.7.
How much?
16.7.
I didn't get it. Please once again.
16.7.
16.7. Okay, let us wait for the other friends.
17.05.
17.05. Okay. Then Guncha Fatma, where you are doing wrong? Why there are two difference? Yours is 16.5. You told probably. Vishal is saying 17 point something. Let us verify with some other friends. It will come around 17 point something.
So 17.2.
17.2 something, yes. So now see, it is a fuel dependent parameter, no doubt stoichiometric air fuel ratio. There is some different kind of the fuels. So depending upon the which fuel you are using, okay, obviously you have to find it out first of all the what is the chemically correct air fuel mixture for a given fuel, and that is the fixed parameter. So once that parameter is known to us, okay, where it is at. Then we know that for a given fuel, what is the stoichiometric air fuel or air fuel mixture or fuel air mixture. Experimentally, we will measure that what is the mass flow rate of the air and what is the mass flow rate of the fuel. Take the ratio. If you are taking fuel by air ratio, it will give you the equivalence ratio, or if you are taking the air by fuel ratio, it will give the relative air fuel ratio or lambda. So either the equivalence ratio or lambda. Okay. Let us talk about the lambda. If the lambda is coming 1, if lambda is coming 1, what does it mean? Sorry. If you are measuring the fuel and air, you have calculated the stoichiometric air fuel ratio. You are taking the ratio air by fuel ratio and finally calculating the relative air fuel ratio or lambda, and that is coming 1. What you are understanding? What is the meaning that your engine is running at lambda is equal to 1? What we can say?
Sir, we can say that there is what we have considered as an equation that is only the input and the output.
No, and okay, that's fine. So lambda is equal to 1. It means your engine is running at a stoichiometric air fuel ratio. It is a chemically correct air fuel mixture ratio. Okay. If lambda is less than 1, or let us think about lambda is greater than 1. Okay. There are two conditions. Lambda will be either 1 or lambda will be less than 1 or lambda will be greater than 1. Lambda is equal to 1, that is fine, that our actual air fuel ratio and stoichiometric air fuel ratio is the same and engine is running at the stoichiometric air fuel ratio. That in that case, your lambda or equivalence ratio, both, it will come 1. But now there is a situation, okay, in which engine is running at certain operating condition. We are measuring air and fuel and calculating the lambda. And then we are doing all these calculations. We are finding out lambda is coming greater than 1. Let us suppose 1.2. What we can say? What we can interpret the value, physical meaning of lambda is greater than 1.
Where there is excess higher than what is required.
There is excess air than what it is required for the correct air fuel mixture. Excess air, it means it is a lean mixture. If lambda is less than, lambda is greater than 1, it means it is excess of air. Excess of air, then it should be compared to the stoichiometric air fuel requirement, air requirement. So in that mixture is called lean mixture. So lambda is greater than 1. It means lean mixture. Air is more than the fuel compared to the stoichiometric ratio. If lambda is less than 1, then what kind of the mixture it is? If lambda is greater than, lambda is less than 1. Then what we can say?
We have excess fuel.
Excess fuel. Then that mixture is what we will call that mixture? It is a rich mixture. So the fuel and air ratio, or the mixture of fuel and ratio, there are either it will be rich mixture, lean mixture, or stoichiometric mixture, depending upon lambda values. If lambda is equal to 1, then it is a stoichiometric mixture. If lambda is greater than 1, it is a lean mixture. If lambda is less than 1, it is a rich mixture. Similarly, you can also analyze equivalence ratio. If the equivalence ratio phi is 1, a stoichiometric mixture. If phi is greater than 1, it will be rich mixture. If phi is less than 1, it is a lean mixture. It is this phi and lambda, it is going to be reciprocal. So you have to be very, very careful. And this kind of this is very, very fundamental things. And that I would like that all of you have a very, very clear concept that what is the difference between the equivalence ratio and the lambda. In which in equivalence ratio, we take the ratio of the fuel and air. And during the lambda calculation or relative air fuel ratio calculation, we take air by fuel ratio. And then when you are doing the calculation, when you will do the experiments, you have to find it out that at which kind or what is the value of lambda or equivalence ratio on which your engine is running currently. For that, we need to measure the actual mass flow rate of the air, actual mass flow rate of the fuel. We already know that which kind of the fuel it is. So we know what is the stoichiometric fuel air fuel ratio. For gasoline, the stoichiometric air by fuel ratio is something around 14.7. 14.7. In your gasoline engine, that ratio is 14.7. When when you see the in a book or any technical paper, you will see that there are so many graphs that has been plotted against the equivalence ratio or lambda. It is very, very critical parameters that is going to define your whole performance, combustion and the emission parameters. That what is the at what ratio or what is the ratio or what is the equivalence ratio phi or lambda on which the engine is running, whether it is a lean mixture, rich mixture or a stoichiometric mixture. So is there any question related to here regarding the air fuel ratio or lambda or phi? Any question?
Sir, in lean mixture and rich mixture, there will be undesired products.
In all three situations, if you are talking about the actual combustion, okay, then in all three conditions there will be undesirable products, emissions, undesirable products. This what we were studying here, this combustion equation, it has a lot of assumptions. It requires a lot of time to complete the whole combustion within the given condition. Actual combustion is taking place in a very, very small time. Okay, so in all three conditions, whatever the product we are seeing here, it will be completely different. It will contain carbon dioxide, water, carbon monoxide, different hydrocarbons. Okay, some amount. Nitrogen will come. Your oxides of nitrogen will be there. Okay, so undesirable. These are in actual combustions in all three situations will be undesirable conditions. Some of the undesirable conditions will be more or less depending upon lean mixture is running or rich mixture is running, on which mixture your engine is running. But undesirable products will be always there for all three conditions.
So we will not take in account in stoichiometric fuel ratio. No?
When you are not taking the consideration.
Sir, the additional products in stoichiometric fuel ratio.
No, here we are talking about in these equations, we're talking about the stoichiometric mixtures. So and it is an ideal combustion equation. So therefore, we are taking only the assuming that the product will be only carbon dioxide and water and nitrogen. But you can do the actual anyway, it requires several other information also. When we can go very close that if this is the oxygen, air, fuel, air, and what are the different products will come out. Then we need some other informations also, because when we are balancing the elements, then the number of unknown and number of equations will be less. So we need some kind of other informations also to calculate the products. So right now we are not going to the lean or rich mixtures. We are just thinking about lean mixture. Somehow we can do that. Suppose there is a lean mixture. OK, and even though we are considering as the ideal condition and it is a lean mixture, what the changes it is going to be there in this equation? Suppose it is a lean mixture and we are considering the ideal combustion. what changes is going to be here? Anybody can tell me?
Sir, we can take that some excess amount of air will be there in the linear
Yes,
mixture.
absolutely.
So it can be taken as A plus B by 4 plus something C sort of thing.
Whatever.
That
Yes.
C is not taking participation in combustion.
Yes, yes. So here it is what there will be the excess of oxygen will be here in the product. Excess of oxygen will be also there. So if it is a lean mixture, if it is a rich mixtures, then the situation is going to be little bit complicated. Because now we have to consider about the carbon monoxide is also going to be come out. There might be not all the fuel is going to be oxidized because it is a rich mixture. There is a less oxidizer. So the not all the fuel is going to be to combust. So the unburnt hydrocarbons will also come into the product. So that kind of the equations is going to, or that kind of the calculation is going to be little bit complicated, but for a stoichiometric and lean mixture, assuming the ideal combustions, we can do sort of the analysis. All of you, as I'm saying, I hope that it is very clear to all of you that if lambda of 5 is less than 1, equal to 1, greater than 1, why it is coming lean mixture, rich mixture, or stoichiometric mixture, what is the difference, all these things. I hope it is be clear to all of you. If it is not, still we have a 2-3 minute. Please ask the question. You can calculate the stoichiometric air fuel ratio for different fuels also. Take it like ethanol. OK, nowadays the ethanol, some part of the ethanol is already it is we are using it with the gasoline. OK, government of India has also big plan for the ethanol, and then the government of India is also thinking about to utilization of the hydrogen. So you can take any sort of the fuel or find it out what is the stoichiometric air fuel ratio for hydrogen. What will be the for hydrogen, for methanol, ethanol. So please do the practice at your room. OK, so I'm assuming that you don't have any question now.